This lesson is for Advanced Algebra, Lesson 6.3 on the graph translation theorem. We're going to use the graph translation theorem today in two ways. The first way we're going to use it is with the absolute value, and then we're going to do it again for quadratics. Know that a translation is also called a slide. So all we're going to be doing is taking either the absolute value function or a quadratic function and sliding it to a new location. So let's look at what the graph translation theorem actually says, taken from page 387 in your book. If you're working with regular x's and y's in a sentence or an equation, then you'll replace the x by x minus h and the y by y minus k to translate it. The h value will tell you which way you're moving it horizontally, and the k value will tell you which way you're moving it vertically. And then when you do that, you'll be using the translation capital T, and then the subscripts here tell you how much how much h and how much k you're going to move it. So let's look at it with an example. If they ask you to find the equation for the graph of y equals absolute value of x under this translation, that means you're going to move it 4 to the left, because a negative number horizontally would mean to the left, and 2 up, because a positive number vertically would move it up. So let's see what that would look like. So it'll translate 4 to the left and 2 up. Here's the original parent function. Here's the original absolute value graph, which looks like a V. And then if I move that vertex 4 to the left and 2 up, then I can redraw my new graph. So now they want you to find the equation for that. So for the equation, we're going to replace the x with x minus h. So if I take my absolute value and plug in x minus what the h value was, I would have x minus a negative 4 inside the absolute value symbols. I would do the same thing for the y, except I do y minus k. So the y is going to be y minus 2. Keep in mind that a lot of times we write these in other fashions or other formats. Most of the time when we do subtract a negative, we change that to plus. So if you see x plus 4, that just means we took away a negative. Also, we like to a lot of times have the y solved so that the y is alone. So then you would just bring that 2 over and make it a plus 2. Most of the time, and when you do this again next year in FST class, the way that we're going to do it is with the y being by itself. So the question then is, how come it's a minus when you plug it into the equation? The equation's trying to get back to what it was originally, so if you move it to the right and down, it'll go back to what it was. That's why we're doing kind of the opposite sign for each of those numbers. So now I want students to give this a try on their own. This is number 4 in your homework. Again, you're working with the absolute value function as your original parent, and then they're giving you a new equation, and they want you to come up with the translation. Well, first just describe how they're related and then come up with the actual translation. So pause the video, give that a try, and the answers will be displayed here shortly. So if you look at the parent function here of y equals absolute value of x, we change it into y plus 1 and x minus 4. So if you think about which way it's going to move the opposite of what we're seeing in the equation. So if we're doing a minus 4, that means the 4 was the h value, so that's moving to the right. And the plus 1 there came from subtracting a negative 1, so that means we were moving 1 down. So then taking those ideas and applying them to the translation map, we'd do a capital T, and then we just do little subscripts, making sure to put the h value first and the k value second. I guess one thing we could do before we move on is just talk about these horizontal versus vertical. If you have a positive number, that'll move to the right. Negative number will move left, and then similarly for vertical, positive number will move up, negative number will move down. So just keep that in mind when you're talking about which way it's going to move. So let's apply this now to quadratics. So when we're working with a parabola and we translate that, there's a piece to that that's super important, and it ends up turning into what we call the vertex form of a quadratic equation. So this isn't the official name of what we're doing today, but that is what it turns into. So the theorem itself is called the parabola translation theorem, but what we get is the vertex form of a quadratic. So let's see what happens. Here's your original parent function, ax squared, and if you apply the translation to it, again you apply it in the opposite fashion like we did previously. So we do x minus the h value and y minus the k value, and that's going to turn into our new translated parabola. Keep in mind that if you solve for for y so that y is alone, the k moves to the other side. What's nice about this formula now is the h and the k tells you your vertex. So h comma k is now the vertex of the parabola. Remember that the vertex is either the minimum point or the maximum point, depending upon which way your parabola is going. It'll be a maximum if the parabola is pointing downwards. It'll be a minimum if the parabola is pointing upwards. So the location of that vertex is the h and the k values, but which way your parabola is going is dependent upon the a value. Positive a is going to point up, negative a will point down. So pay attention to that value as well. All parabolas have an axis of symmetry, and the axis of symmetry will be a vertical line that cuts through every parabola. Since the vertex is either the minimum or the maximum point, the axis of symmetry, that vertical line, will cut through that vertex. So if you know where the vertex is, then you can identify where the axis of symmetry will be. So it's a vertical line through the vertex. If you know where the vertex is, then you know the h value. Just say x equals h and you'll be able to give the equation for the axis of symmetry. So let's put that into practice now with our first example here. So we've got this equation, y minus 5 equals negative 2x plus 3 squared. What are all the things you know about this equation? So it came from the parent function negative 2x squared. If you get rid of the 3 and the 5 there, that's what you're left with. And it got translated 3 to the left, because normally this would be a minus negative 3. And it translated 5 up, because we took away a 5. So 3 left, 5 up is how it got translated. The original was negative 2x squared. The vertex then is going to be at negative 3 comma 5. 3 left would be a negative 3, 5 up would be a positive 5. And then once we know the vertex, we know that the axis of symmetry is going to cut through this number. So we just say x equals whatever the x value is at the vertex line. And we know that that vertex point is going to be a maximum because the a value is a negative. So now I want students to give it a try. Questions 8a and 9a ask you to identify the vertex and the axis of symmetry for this equation. Go ahead and give that a try. Pause the video. Answers will be displayed shortly. So when you're writing number 8a, take the opposite of what you see here, so that's a negative 5. Opposite of what you see here, so that's a positive 7. So the vertex is at negative 5 comma 7. And then for the axis of symmetry, you have to have the vertex in order to figure that out. So you just take x equals, and then you just grab the x part of the vertex.